This will go away.
Okay, very good. Yeah, yes, okay.
But there's still a few folks.
So maybe you will say a few words.
Yes.
Okay, I will wait.
That's fine. That's fine. Okay. Well, thank you for everyone online, and thank you for everyone coming in here. Good morning. My name is Florence Bouquet. I'm the Managing Director for CREW, the Center for Research and Education in Wind. Today's seminar is given by Wenzhong Gao from Denver University. Dr. Gao is an Associate Professor of Electrical and Computer Engineering, and he's the Director of Renewable Energy and Power Electronics Lab. Dr. Gao holds a BS degree from Northwestern Polytech University in Jiang, China, an MS degree from Northeastern University in Shenyang, China, and a PhD degree in electric power engineering from Georgia Tech. Dr. Gao currently serves as an editor for IEEE Transactions on Sustainable Energy, and he has been an active reviewer of leading journals and conferences such as the IEEE series of research, and among others. Dr. Gao has conducted extensive research in areas of power and energy systems, including renewable energies, smart grid, power delivery, power electronics application, power system protection and restructuring, and hybrid electric vehicles. Today, Dr. Gao's talk will be about wind energy integration, applications of energy storage systems, and wind power fluctuation smoothing control. Welcome. Thank you.
Thank you. Thank you, Florence. And thank you, Dr. Lucy Powell and the crew for giving me this opportunity to present, to talk about about my research. So today the topic is wind energy integration. In particular applications of energy storage system and wind power fluctuation smoothing control. And so this is the outline. First, I'm going to talk about my research background, in connection to renewable energies and the smart grid. Then I will discuss the wind integration challenges, and after that I will do two highlights of my group. The research. One is the energy storage systems, the application of energy storage system, and then the second is the wind power fluctuation smoothing control. So basically, these two topics are related to fluctuation control, both. And then I will do a conclusion. So about my research interests, I'm interested in integration of alternative renewable energy sources into power grid, particularly wind power and solar power. And I like to study system impacts of intermittent sources on power grid. So some specific areas I'm interested or have been doing is application of energy storage systems to counteract wind fluctuation and wind variability. I have another research interest, which is power system protection and control using wide area monitoring systems, WAMS. Nowadays, we have, or DOE have spent a lot of energy to deploy PMUs, phasor measurement units, so that we have a wider view and also control of power systems on a larger scale. Also earlier on, I also had some interest in hybrid electric vehicles. For a few years, I did some research for hybrid electric vehicles, and now, because of the smart grid, so my prior research in hybrid vehicles now can also be used for studying smart grid. I will talk about this a little bit. And so my overall goal is to understand issues and find new solutions related to renewable energy and smart grid. And my teaching, okay, right now I'm at University of Denver. I'm the primary faculty, or you can say probably only faculty in the power and energy areas. So I came to University of Denver in 2010, and I developed a whole curriculum in power and energy systems, and we have 5 or even 6 courses. I teach 5, but we have 6 courses in power and energy systems. And I teach, for example, Introduction to Power and Energy Systems, which I'm teaching right now this quarter, and also renewable energy and distributed generation, which also this quarter I'm teaching too. And then next quarter I'm going to teach power system analysis. And in the spring I teach power system operation and control, and in alternate year I teach power system protection. And also I teach like power electronics, but on a smaller scale. And previously also I taught hybrid electric vehicles. So I want to talk a little bit about the renewable energies, but in the context of smart grid. So my view of smart grid, really we have three components or 3 subsystems in smart grid. So we have smart power generation, we have also smart transmission distribution, and also smart choices in terms of demand response. We have heard a lot about smart grid, especially in Boulder. I think Boulder, the Exo Energy has done some experimental smart grid. But mostly are on the the smart choices on the customer side. And so my interest here, smart power generation. Okay, so basically, for example, renewable energy can be a significant portion of the future power generation. As we know, in the past 5 years in the United States, in fact, the new power capacity coming online are mostly from wind and solar. We have much less conventional power generation. Okay, I'm sorry. We have much. Okay. So we need to make the generation to be smarter. Okay. So that means we need a better control. I think I have okay. So basically, we need smart controls for power generation and even for power transmission distribution, right? So basically, for transmission distribution, how do we achieve a smart network? That's why we need WAMs, or phasor measurement unit, PMU. So PMU-based WAMs can help us achieve smart transmission distribution. And on the customer side, of course, we can have two-way communication and load control to, in conjunction with real-time electricity market, pricing information to help customers making choices in terms of when to consume electricity and where to consume electricity. So renewable energy integration, we have many different technologies. For example, of course, obviously wind energy, solar, hydro also. But hydro is more like kind of traditional renewable energy. And another thing is plug-in hybrid electric vehicles will become a significant player in the future, near future, in terms of integration. For example, the the plug-in hybrid vehicles can help integration of renewables like wind and solar, especially wind. For example, in the night, when we have a lot of wind, and then this hybrid or plug-in hybrid electric vehicles can help help absorption of those wind energy in the night, right? And then in the daytime, we have the hundreds or thousands or millions of plug-in hybrid electric vehicles which are connected to the power grid. So during the peak time, we can use, for example, V2G, vehicle to grid technology, to help the grid during the peak time to avoid issues. And another thing about integration is that we have complementary behavior or characteristics from wind and solar. So this green curve is wind power production over 24 hours, and then this line, orange line, is solar, right? Solar power production. So they kind of complementary. They are kind of complementary to each other. So I mean, theoretically, we could get a overall renewable energy from wind and solar. Overall production is kind of we can shift down the current load, like in parallel. So the utility side can have a better control because they are very familiar with this load profile. Unfortunately, we cannot get such ideal behavior right now from the wind and solar. The reason is because we have a lot of wind, but a relatively lower amount or smaller amount of solar. So that's why we are going to see more and more solar power coming into the grid. So overall, we can achieve a better integration of wind and solar. So wind energy, as we know, DOE has a kind of a goal, ambitious goal of achieving 20% of wind energy by 2030, right? By 2030. And there's a report in 2008 coming out from the DOE study, and so this goal can be achieved, but of course there are some technical challenges, and other challenges, right? Transmission challenges, and so one challenge is, for example, is to prevent blackout as we integrate more wind into the grid. And so what are the challenges? What are the challenges? I think there are more. There are two main challenges. One is that we do not have enough flexibility in the conventional power grid. Especially in winter and spring, when the wind is high, but we don't have enough coal-fired power plants to accommodate wind. The reason is that the coal-fired power plants do not have enough flexibility, especially in terms of the ramping rate. So maybe in the future we need a little bit more of the gas-fired or natural gas-fired or oil-fired power plants to accommodate more wind integration. And the second challenge is that we do not have enough transmission capacity, because of the wind typically on the far end side of the transmission grid. So it's relatively weak at the wind location. The grid is relatively weak, and we don't have very strong transmission capacity. So solution one is that we can create a larger area regional power balancing grid company, so that we can consolidate the flexibilities available on a larger scale to help wind integration. Second, we need to build dedicated high voltage transmission corridor from, for example, from west to east. And so wind turbine generator system. So this is an overall picture of a wind turbine generator. So we have wind power coming through the aerodynamic blades. And then we extract wind power and we get mechanical power through the gearbox. And then the electrical generator will get power and produce electricity, and going through the power converter and transformer. And then this wind power is finally connected or integrated to the power grid. And then we have 4 types of wind turbine generators. Of course, we know squirrel cage, one rotor induction generator, but nowadays 60 to 70% of deployed wind turbine generators are doubly fed induction generator. In the near future, we may see more permanent magnet type, permanent magnet based generator in the future. We may see more. Wind power integration, we can integrate wind power on several, sections or several parts of the power grid, because power grid is, categorized or divided into transmission grid, subtransmission grid, and also distribution level. So depending on the level of your wind power plant or wind farm. If it's very huge or big amount of wind power plant, we can integrate them into the transmission grid. And then if we have a relatively smaller wind farm, we can connect those wind farm or individual wind turbine onto the distribution level. And of course, smaller wind turbines like community wind turbines, or we can put directly in the distribution network at a lower voltage. And then what are the differences? Differences between conventional power generation and wind power generation, right? In the conventional power generation, we have a single or a few large generators, very huge power generators. Typically, our synchronous machine, synchronous generators. But on the wind side, we have hundreds of smaller wind turbines. I mean, smaller means in the range of 1 megawatts to 5 megawatts, comparing to the large conventional synchronous generator. And so for example, controllability of conventional power generators are much better than wind, because on conventional generator we can ramp up and ramp down, right? We can control the generation to be more or less depending on the load, right? But on the wind side, we can only do curtailment. So on the other hand, we can do a little bit of other control by inertial control and other frequency control. I'm going to talk about this. And predictability is different. Conventional power generation, we can predict very well. We can plan very well, right? And we can do economic dispatch. But for the wind, we can do short-term prediction, but for longer term, like a day ahead and even weeks ahead, it's very difficult to predict. So so that means we can we need to do some research, for example, in terms of wind power generation. We can do some research about collector system design, optimization of the collector system, reactive power management, voltage regulation at point of common coupling or common point of integration. And also we need to do research about AC or versus DC power transmission from the wind. And also so basically the integration, when we integrate wind, we need to keep balance. We need to keep balance of real power, reactive power in balance. So when we keep real power in balance, we can help with frequency. Frequency control or frequency regulation. And on the other hand, if we can keep the reactive power in balance, we can keep the voltage constant. Okay, that's very important two aspects of integration: frequency and voltage. So, so if we look at the power balance of real power, okay, if we like a balloon here, okay, real power. Okay, if we look at real power, so the loads, if we have more loads, if we have losses, right, all this will push this balloon down. Okay, and then if we have more generation, if we put more injection of the power from the generators, from the conventional generator, from the renewable energy generator, right? Then we are pushing this balloon up, right? So at every instant, we have to maintain this balance, okay? So that we can maintain the frequency. Otherwise, the frequency will go up and down if we have a mismatch between the real power and the load, right? So that means, you know, that's why we bring the storage into this picture, because energy storage can help this balancing of the real power, real power balancing. And balance, I mean, energy storage can come into the line very quickly, and so that's very helpful. So on the right side, we have reactive power balancing. Similarly, okay, there are some reactive power load. For example, line, the transmission line, distribution line. You know, the line inductance are typically reactive load, right? And also on the consumer side, we have inductive load also, like induction motors. Induction motors consume like about 60% of all the electricity. And even induction generator, like the wind turbine generator, they consume reactive power, right? So all these loads, reactive loads, will push this balloon down, and then on the other side, we have, you know, line capacitance in the lines, and we can switch capacitance online, and also synchronous generators or synchronous condensers can also, you know, provide reactive power or reactive source, right? So all these provide reactive sources and can push this balloon up. So basically, we have voltage up, and, you know, if we have mismatch about reactive power consumption and reactive power generation, then this voltage will go up and down, right? So that's, you know, people are developing static compensation technology, like fax devices, to help maintain the reactive power balance. So with the wind power integration, we will have both issues on the real power balancing because of the fluctuation of the wind, and also reactive power balancing issue because of the, you know, consumption by the wind generator, right? The reactive power consumption, and also transmission of the reactive power from far away to the load, that will add additional reactive load, right, to the grid. So both are the kind of issues. So I mean, we have talked about wind power variability, right? So energy storage can help, you know, if we have energy storage, we can help to counteract the variability issue. Also, the transmission constraints will make the wind power transmission from the wind to the load center kind of more difficult, and then energy storage can also help this. Another thing is how to match wind and load in smart grid scenario. We know the demand side management in smart grid, right, can shift the load peak away from the away from the peak time, and also in the future we can also control plug-in hybrid vehicles charging, discharging to further shift the peak demand. So so by using energy storages, we could potentially shift the wind power generation. For example, wind power generation are high, for example, in the night, right? So energy storage can help, help shift the power production, so that wind power can better accommodate load during the peak times. And wind power plant really, here this as you see the variation, the variation here during a day, during like 24 hours period, is really a lot of variation. But on the other hand, also a lot of ramping, for example, ramping events. We can see a lot of wind power generation or wind power reduction because of the rapid change in wind speed sometimes. So that can be a very big challenge for the grid, for the power grid, to handle those ramp. That's why we need larger areas, larger balancing areas, so that we can aggregate the variability and do better balancing control. And so the one research challenge is the low voltage ride-through. Low voltage ride-through. So low voltage ride-through means, when the in the grid, power grid, we always have different faults. Power system, short circuit may happen from time to time. So in the past, wind turbine generators can be disconnected from the power grid. But as we have more and more wind turbines coming to the power grid, connected to the power grid, the wind turbines have to be connected to the grid even during the fault events. In fact, there are very strict grid code. For example, FERC, the United States FERC, has an order 661A, requires that the wind turbine machines has to be able to ride through up to 9 cycles at 0 voltages at the connection point. At the connection point. So that's a challenge. So low voltage ride through. So the sudden disconnection of wind turbines can affect system stability, right? With more and more wind turbines coming to the line, this may become even severe, this effect. So we need to develop low voltage ride-through technology to keep, for example, double-fed induction generator or permanent magnet wind turbine generator connected to the power grid during the point of interconnection, POI bus voltage dip, without, there are two concerns. One concern is we don't want to destroy power electronics in wind turbines. The other concern is we don't want to affect system stability during those events. So we have done some research in this topic area, develop different low voltage ride-through technology to help. And the control challenges, as we said, difficulty in balancing control due to variability and uncertainty of wind power and systems, stability issues, right? So the solutions is that we need to develop innovative control methodologies. Especially we need to develop hierarchical and multi-level control, and I will show you later in a picture. And also we need to develop voltage stability control, frequency stability control, and also we need to develop smart control on wind turbines. We need to integrate wind forecasting technologies into the economic dispatch of wind power, and also load control. And another very promising solution is that we can use energy storage. Okay, but in a distributed way. I will show you a picture which here. So this is a proposed kind of solution idea to help integration of large-scale wind into the power grid. So what we call multi-level coordinated control. So basically, power grid or wind power integration, really we have three levels. Okay, three levels. Level 1, and then level 2 and level 3. So level 3 is more on the individual wind turbine, level, and level 2 is on the wind farm level or wind power generator level, wind power plant level, and then level 1 is more on the power balancing level. Okay, power balancing authority like the Xcel Energy or a big power grid operator like WAPA, okay, Western Area Power Authority. So we have different level. So the control of the wind power integration can happen, okay, at all these different level. For example, at level 3 on the individual wind turbine, we can do better control of real power, reactive power, right? And then on the wind power plant level, we can control, again, real power, reactive power management, and to help balancing the real power, reactive power, and also the voltage control and frequency control, right? So it's more here. So we need to control voltage and frequency at the point of interconnection of the wind power plant, and of course on the larger level, on the utility scale, we need to have more like wind power forecast, and also power market and even load, right? All this information should help the utility operator to achieve intelligent system level control of the wind power. In fact, the Xcel Energy, they during the high level, they can even have 40% of wind power. 40% of overall wind power, comparing to the total generation. Okay, so that's a lot of wind. So that means we need to again maintain real power and reactive power balancing, so that we can control frequency and also control the frequency and also the voltage control. And and on this different level, we can use energy storage. Okay, we can use energy storage. For example, on the individual wind turbine, we can use energy storage. On the wind farm or wind power plant level, we can use energy storage. And even on the system level, we can use energy storage. For example, hydro power plant, right? And then now let me move on to one research topic we have been doing. Is the hybrid energy storage systems, but in particular we use a probability-based method to design the power capacity of the, for example, batteries and supercapacitors. In renewable energy generation, the use of energy storages can be found, mostly in lower power levels, such as the small wind turbines, right? In the utility size of wind turbines, the energy storage systems can help the ramp rates and also help smooth out the power fluctuations, especially in a weak grid. Together with electric transportation, such as electric vehicle and plug-in hybrid electric vehicle, in the near future, the cost of energy storage system will be reduced, and this technology of using energy storage looks very promising. And in fact, there are many different energy storage technologies available for our consideration. Like a large-scale pumped hydro storage, can be used by utility scale, like X-Energy or WIPA. And okay, even here, compressed air energy storage, can be also at a higher level. But like flywheel energy storage systems can be implemented on a wind power plant level, like near the wind farm. And also the flow battery, for example, can be also installed on a wind farm, right? And on the other hand, we also know that we have lead acid batteries, we have lithium-ion batteries. Those kind of batteries are becoming cheaper and cheaper. And in fact, the DOE is investing a lot of money to do research to help bring down the cost of different battery technologies. And so batteries and supercapacitors really can be very helpful for wind energy integration. And this is a kind of a case, a real case in Japan, in a wind power plant. They use I think flow battery to help smooth out the power output from the wind turbine, right, or from the wind farm. As you see, this the orange, the pink line is like actual wind power plant output without in fact here this is okay without batteries or without energy storage, right? It's a lot of fluctuation, but this green line, green line is kind of the power delivered to the power grid, so it's a straight line. So the power company likes this kind of wind turbine behavior, but then we put a lot of burden to the load. To the batteries. You see, so this fluctuation, all this fluctuation up and down, are absorbed or accommodated by the batteries, by the energy storage systems. So this is just an example in real life. And what we did is that we want to put a hybrid energy storage systems here. For example, for Type 4 machine, we put a hybrid energy storage system, meaning that we put batteries and supercapacitors in parallel. For example, we put in the DC link, and so we provide a power buffer between the wind turbine and power grid. Okay, so the goal is that we want to deliver constant power dispatched to the power grid, and whatever the fluctuation will be accommodated by the energy storage systems. But one issue is that how do we design the energy storage systems? We don't want to oversize the battery or supercapacitor, because that we will add cost to your energy storage system, right? On the other hand, we don't want to be too small, the energy storage size. So how do we do it in a correct way? So we started looking at the profile of the wind power fluctuation, and then we do wind power fluctuation, right? And then, for example, this PD, this straight line is a PD, what we call the dispatched power, and this fluctuation is wind power, PW. So PD is like the desired power by the power grid, okay? And so the difference will come from the batteries or energy storage systems, right? So this fluctuation, goes to the energy storage systems, and then in fact, we can take the absolute value of this fluctuation, and we can see here. So if we design the batteries just based on this fluctuation, right, we will see that we need, for example, 0.5 per unit of batteries in terms of power capacity needs to be designed, right? That's like a very high, okay, very high capacity for the power for the batteries. So and also we have a lot of fluctuations. The fluctuations will reduce the battery life. So one issue is that when we use energy storage or batteries to help wind, we don't want batteries to see all this fluctuation all the time, because the battery has a cycle life, right? So we have to consider that. So our idea is that we want to use a supercapacitor. For example, supercapacitor can accept a lot of fluctuations, and they have very high cycle life, like millions of cycles, charging, discharging. So basically we do a statistical or probability modeling of this fluctuation. So and then I'm going faster because we're running out of time. So okay. So we do, for example, a histogram analysis of those the power required from the energy storage systems, right? And we can see that a lot of the fluctuation, a lot of the fluctuations are concentrated on the lower power, kind of relatively lower power level, and the higher power fluctuation, for example, 0.4 per unit, 0.5 per unit, the relative higher power fluctuation, it happens less frequently, right? Less frequently. So I mean, we can use a kind of a PDF, power density probability density function, to approximate this histogram model, and then we can come up with a model of this fluctuation, right? Needed by the energy storage systems. And then we say, we want to, for example, to use batteries to accommodate, okay, up to 0.37, okay, so up to 0.37 per unit of the fluctuation, right? Of the fluctuation, and then this, actually will take care of about 95%, okay, of those fluctuations, and the leftover, like 5% fluctuation, which happens at high power fluctuation, we will use supercapacitor to take care of that, okay, So that's our kind of method to design the hybrid energy storage systems. So basically, this is your cumulative probability function, and then we said we find 95% of the fluctuation, and we assign the batteries to take care of that, and then we whatever left, okay, subtract whatever left, we use capacitor. CPC means capacitor. Okay. So that's our kind of design based on the probability-based design. And then one question we may ask is that, then what kind of PD should we assign for the wind turbine or wind farm to deliver to the power grid, right? It may be 0.5, 0.6, 0.7, right? So obviously there's an optimum one, right? Which also will affect your battery design or capacitor design, right? So that the PD should be optimized. So we come up with a benefit function, in terms of the power benefit, the economic benefit, the cost, and then we optimize that function, and so that we reach a kind of maximum or optimum benefit, and then we get a corresponding PD, okay, the delivered power to the power grid. Of course, it's constant. So that is the idea. So to achieve the maximum economic benefit, we should maximize the profit, by dispatching PD to the power grid, right? So that is the idea. And then and based on that, we design the capacity of the batteries and the supercapacitor. So now we did a case study. For example, this is a wind power profile, highly fluctuating. Okay, highly fluctuating. And then as we see, the PW is the wind power. It varies from 0.35 per unit to 1.41 per unit. For example, this is a 2 megawatt wind turbine generator, right? So the per unit means 2 megawatts is your base. Okay, is your base. So the wind power fluctuates a lot. Wind power output fluctuates a lot. And then based on our PD, for example, PD is the 0.9, okay, 0.9 per unit is the power we want to deliver to the power grid at constant power. So the power grid does not see the fluctuation at all. So whatever the fluctuation will be taken care of, okay, PESS, P sub ESS means energy storage systems, the power, right? It fluctuates, positive, negative. Positive means the battery is being charged, and negative means the battery is being discharged, okay? So that is the cycle. And then so we do the statistical modeling of those fluctuation, and we come up with this PDF, and then as I said, we assign a confidence value of 95%, okay, for the batteries. So we size the battery energy storage system, the power capacity to be at 0.37 per unit, which is about 740 kilowatts hour power capacity for the battery, right? And then the leftover, which is 0.18 per unit for supercapacitor, okay, which is 360 kW. So this is the design of the hybrid energy storage system. And then this is the as we see, if we only use battery energy storage system, then we can see that the battery will see a lot of fluctuation of charging, discharging. So that's not good for the battery life. Okay, not good for battery life. But with the hybrid energy storage systems, as we see the battery here, the battery power, as you see, it sees much less, charging, discharging fluctuation cycles. So it will help battery life extension. And in fact, we can look at the battery state of charge, and also, this is supercapacitor state of charge, and then we can do different. In fact, we are doing further analysis or design of how to design the energy capacity, because that method is only for power capacity design, but also we need to look at energy capacity, right? In terms of how much energy you want to store. Okay, another topic I want to show briefly is about wind power fluctuation smoothing control. As we have more and more wind, like higher wind power penetration, frequency deviation will become an issue. Frequency deviation due to the wind power fluctuation will be a key issue in the future. So we need to look at the frequency control, or but from the smoothing control aspect. Okay, as we know, we always want to extract the maximum power from the wind turbine. That's one goal. So basically, we can have an optimal speed of the rotor, right? By looking at the power curve. So we can control the wind turbine generator to run at optimum rotor speed, right? And then we give that rotor speed to the to a PI controller, so that we can get your optimal real power, right? Real power reference to the controller of the generator. So our original purpose, in fact, we have a speed limiter. You have to limit the reference speed of the rotor speed, right? So for example, limit the rotor speed from 0.6 per unit to 1.3 per unit, right? And so our original purpose is to make sure it's secure, it's safe for the rotor, right? And the rotor will not over speed, or okay. And then in fact, okay, we can by optimizing this upper limit. This is upper limit in the limiter, omega max, right? We can optimize this guy so that we can achieve a smoothing control purpose. That's what I want to. Okay, I want to show you here. So depending on the different upper limit of that speed controller, right? So upper limit 1.3, 1.1, 0.9, and 0.7, and this is the power output, right? The power output. As you see, the slope and the derivative of the slope of the wind power output as a function of the wind speed, changes, right? As we reduce that upper limit omega max, we see a much reduced derivative. That means we see less fluctuation, right? Because this delta PW is the smoothing. I'm sorry, is the fluctuation from the wind power, right? So because of the wind speed fluctuation, right? So basically, we can kind of, by tuning down the omega max, we can achieve a reduced fluctuation. Some people have done, have looked at this. It's called deloaded control of wind turbine, and you can use this deloaded control for frequency control purpose, right? So that you can upgrade, right? Up to the provide up. 5 minutes, okay. So yeah, 1 more minute. Two more minutes. Okay. Anyway, so basically, if that's how. Okay, I showed you here. So basically, the power fluctuation will come down. So we did some research on this side, but the one problem is how do we estimate the frequency deviation? Because we don't want to put too much reduction. Because if you tune down the upper limit of the rotor speed, right, you're equivalently reducing energy production, right? So we need to achieve a trade-off between the smoothing control and the energy harvest or the spillage. We don't want to spill too much energy. So there's an optimal way. Optimal way is that we need to look at the frequency deviation caused by the fluctuation. So we developed a framework to estimate the frequency deviation risk. The power company always set a limit for the frequency deviation. For example, 0.5% usually, okay, 0.5% deviation from the 60 hertz, for example, right? So we need to estimate so that we don't go over or go violate that speed deviation limit for the power company. So we can estimate the frequency deviation, as we see frequency deviation under different omega max by tuning down the rotor speed, right? So we can look at that, and then we can achieve smoothing control. So there's an optimization going on, and then we can, as we see, the frequency is here. By doing that control, the frequency is maintained within that 0.5% range, okay? And then and overall. So anyway, I ran out of time, but we can do also frequency control and other stuff. But okay, maybe let me stop here. And I don't know if you have a few questions. Yes. Okay, what is the question?
I was wondering, it looks like you're designing batteries and capacitors to go on individual turbines.
Yes.
And I thought once we connected all the turbines in the wind farm, the power would already be a bit smoother. So I'm wondering if you considered putting that storage after the connection.
Yeah. You're right. We can put energy storage on the wind turbine generator, but also we can put it in the wind farm level. Yeah, combining. For example, wind farm level, you can use the hybrid, not hybrid, flywheel energy storage or flow battery, and so we can do trade-off.
So why is it ever better to do storage at the single turbine scale? do it at the front?
I think at individual wind turbine level, we can do some, like for example, real power control better. Yeah, real power control.
You can also use it for braking.
What? Braking? Or using the
for overspeed conditions.
Okay, overspeed or even low voltage right through, help the low voltage right through. Low voltage right through. Yeah. So there are some benefits. Yeah. Oh, yeah.
Are you at the stage where you just have a model of a capacitor and a supercapacitor battery?
Yeah.
Or have you actually gone out and done a feasibility in terms of cost of energy? Have you gone out and like chosen a specific manufacturer?
No, no specific manufacturers, but we did some economic analysis. Yes, is it economical? Yeah, yeah, and also control how to control the batteries, the charging. In fact, this is just the sizing design, but also we did some research. We probably have 2 or 3 papers how to control the battery and the supercapacitor, the charging discharging, so that the battery, yeah, and also economical, so that the cycle life of the battery will not be affected. Oh, yes.
Question.
Yeah.
So in the case of the 2 megawatt turbine, where you determined that you require a 700 kilowatt battery,
yeah,
and a 130
kilowatt supercapacitor. Yeah.
What would the cost of that battery generally on?
Yeah, it depends on the batteries depends on the manufacturers. Whether we use lead acid or lithium ion, there are some prices.
Like $100,000, $500,000.
It's on the thousands of dollars, definitely tens of thousands of dollars. Yeah, maybe $200,000, something like.
Is that just the raw battery cost, but also the system required controller, the housing?
The controller is cheap. The controller is not a big issue.
With the cooling, etc.
Yeah, system integration, yes. But the main cost is the batteries. Yeah, controller is not expensive. Yeah, we can do it. Yeah, I can show you. I have one paper for the economics. Yeah, to analyze the cost.
All right. Well, thank you very much. Thank you all for attending, and thank you.
Okay, thank you. Okay. Thank you very much.
Thank you. We're running out of time, so we'll all let you go. Thank you very much.
Okay. There's another class.